Okay, believe it or not, this is the last week before spring break, so we will have classes today and Thursday, and then we'll have a week-long absence from one another. The only reminders I have other than that are, I think the exam scheduler this time opened up pretty early, so you may have already seen it. I don't know if you guys get notified about that or if you religiously check the CASA website. But nonetheless, it is available, so make sure you sign up for a time you like. The next exam is not for a while still. It's still 2.5, 3 weeks away or something like that. But make sure you sign up for a time if you haven't done that already. Just make sure you get a time that works with your schedule. Because that will come up pretty quickly after the break once you enjoy your week off. Okay, so today we're going to continue on with Chapter 6 material, which is all about aqueous solutions and reactions that happen in aqueous solution. And so today we're going to talk about a little bit more about the quantitative aspect of aqueous solutions and then start classifying the different types of reactions we can have. So the first thing we're going to talk about is sort of dovetails from last time, but as I always forget to do, let's talk about this first, which is our weekly sort of work habit reminders. One of the many ways you have to get help in this class if you feel like you need it is in office hours. And I have the regular hours posted, which are every Tuesday and Thursday after class, but I'm available other times in person or online as you need, so please don't hesitate to contact me for times outside of there. I would say at this point, I don't keep close track obviously, but this isn't a huge group of students this semester. And there's probably less than 5 of you that I would call regular office hour attendees, which means you've come more than once essentially. So it's not very many of you that are actually coming. Maybe you guys don't like me, but that's fine. But I still think it can be helpful to do that. But you have to take the initiative. I'm not going to obviously reach out and invite you to those. And then if you do come, and I encourage you to come regularly if you think it's helpful, and for most people it is. Some pointers below on sort of how to best use your time if you're there. So most students that come, they find the biggest benefit is to go over practice problems with me that they had on their homework assignment that they didn't fully understand. Either they didn't get it right at all, or they got it right and they're not quite sure if they did the problem correctly. Because again, this is a problem-based course, so that's usually the best way to focus your efforts is by working on problems and going over them. And so what's helpful to do is as you're going through the homework assignments every week or other practice problems that you do on your own, keep track of all of them and keep track of the ones especially that you don't feel like you're 100% certain about. Because after you've done a bunch, you may not remember which ones you were feeling a little bit uncertain about. Or if you get the answer right, you might be sort of goaded into a false sense of confidence. But as you're doing the problem, just keep track of it and mark it if you think that it's something you're not sure about, and make sure you revisit that, and if need be, revisit it with me in the office hours. And then also, when you come to go over problems with me, it's very helpful if you bring your work with you. So keep track of the steps that you wrote out and that you followed to solve the problem, because then I can help you identify where you might have gone wrong on it. It's sometimes hard if you try to remember from scratch, oh, this is what I did, this is what I think I did. It's harder for me to really identify what you might be missing, but if you keep track of all of that in a notebook and keep it organized so that I can see what you did, it usually makes it more effective. So that's kind of some strategies for best using. But again, however you choose to use that time, I'm always happy to help. So I'm not like Willy Wonka. I'm not going to turn you away if you do something wrong. So just come in if you think it's going to be helpful, and I'll, as I said, set up appointments with you if the regular times don't work. All right, so with that, let's get into the material. So we talked at the end of last time about sort of how to think about what happens when something dissolves in water. This whole chapter is about solutions where something is dissolved in water. And we said the key difference was for covalent compounds, which we're not going to talk about a lot in this chapter. When you dissolve a covalent compound in water, the water molecules surround it, and they make some sort of interactions with it that we'll sort of classify in more detail later in the course. But really, the molecule stays intact. You're not breaking any bonds, or you're not really changing the chemical composition in any way. The difference, though, is when you dissolve ionic compounds or strong acids in water, as we saw, the water molecules sort of grab onto each ion and pull them apart from each other. So in an ionic compound, the water essentially breaks those ionic bonds, separates the ions completely, and surrounds each ion individually. And so you're, again, breaking the ions apart is how you want to think about that. So this first example here looks at that a little bit more quantitatively, which is how many moles of ions are present when 3.00 grams of silver nitrate is dissolved in water. And so when you're thinking about moles in solution, you have to think about what happens to the compound when it dissolves. So if we're asking about the moles of a specific ion in the solution, or in this case, the total number of moles of ions in the solution, you have to think about, again, what kind of compound it is and what happens when it dissolves in water. So the way to think about this is first sort of write out a little bit of a chemical equation for what's happening. So we're starting with silver nitrate. That's the correct formula there. So just remember, our formulas for ionic compounds, definitely in this chapter, is going to come up a lot. So when you dissolve this in water, it's starting out as a solid, as I'm showing here in the photograph. It's a nice white crystalline solid. It doesn't look too different than sodium chloride, but it's much more poisonous. I don't recommend seasoning your food with it. And what you do is you take that and you dissolve it in water. So sometimes what you'll see in chemical equations is just water over the arrow means you're putting it into water. And so when you put this compound into water and it dissolves, again, what happens with an ionic compound is the ions separate from each other. So the way you would indicate this in a chemical equation is that the two ions, so the ions that make up this compound are silver plus 1 and NO3 minus. Again, it's silver 1 nitrate. So you're going to make silver plus and NO3 minus. Those two ions are going to separate from each other. And we write them again with a little AQ next to them to tell us that they're dissolved in water, AQ meaning aqueous in this case. So this is a way to indicate what happens when an ionic compound dissolves in water using sort of a chemical equation to do that. And so then when you're asking a problem like this that's dealing with how many moles of ions are in a solution, the key concept to recognize is that for every 1 mole of silver nitrate we dissolve, we get 1 mole of silver plus and 1 mole of NO3 minus, or a total of 2 moles of ions. 1 mole of positive ions, 1 mole of negative ions. How many ions you get, of course, depends on the formula of the compound you're starting with. Here it's just a 1-to-1 compound with 1 cation and 1 anion. So then when we're addressing the problem at hand, if we're looking for moles of ions, we start with the mass of the compound that we have. And we know very well by now from chapter 5 how to convert mass into moles. But if we use the molar mass that's given to us, 169.87, that's the mass of 1 mole of AgNO3 together as an intact compound. So we're going to use that molar mass, 169.87, to go from grams into moles. But again, we have to keep close track of what that moles represents. So that moles is going to be moles of silver nitrate, but we're looking for moles of dissolved ions. So there's one more step here, because as we said, for every mole of silver nitrate we dissolve, we get 2 moles of ions. 1 mole of positive ions, 1 mole of negative ions, a total of 2 moles of ions. So there's going to be 2 moles of ions for every 1 mole of silver nitrate, AgNO3. And so that last step there is critical to get the correct answer as 0.0353 moles. All right? And this last step here is the one that many of you will forget, or I hope you don't now because I've warned you about it, but this last step is critical when you're thinking about dissolving ionic compound in water and when we're asking about the total number of moles of ions. So when we're dissolving something in water, and particularly if it's an ionic compound or an acid that breaks up, we can define the moles of each individual ion, or we can define the combined moles of ions as we did here, and you have to just pay close attention to what you're looking for to be able to make sure you're using the correct conversion factors. So any questions on that one? Yes?
If it was like a 2 plus and a minus, would it be 3 moles?
Yeah, so if the formula was let's say calcium chloride, and then you dissolve that, you would get calcium 2 plus and then 2 Cl minuses from the formula. So there'd be a total of 3 moles of ions in that case. So yeah, the number you put here depends on the formula of the compound and how many ions it breaks up into when it dissolves. So you have to know the formula of the compound and then separate it into the individual ions that make it up to be able to get this last step correct.
So that's the total coefficient or the total charge?
It's the total coefficient, so it's how many total moles you have. So there's 1 of each, so 1 plus 1 is 2. Here there'd be 1 and 2, so that's a total of 3. So it's the total number of ions, the total coefficients in front of those ions when they dissolve, which you can get directly from the chemical formula as well. This is just showing what happens when it dissolves, but the chemical formula tells you how many ions are in the formula directly as well. All right, we're clear on that. Okay, so that's going to be sort of leading into then the next topic, which is again a more sort of quantitative treatment of compounds dissolved in water, which is a parameter called molarity. So this is going to be a new relationship involving moles, so we're going to put it into our bag of tricks for relationships involving moles, because in chapter 5 we introduced a couple involving mass and number of atoms or number of molecules, and now this is going to be a new relationship that involves moles in solution. All right, so molarity is a concentration unit. It tells you how concentrated a solution is. And we should have some general concept of what that means. If you're mixing salt with water, if you mix a little bit of salt with water, you can barely taste it. If you mix a whole spoonful of salt in a glass of water, it's going to taste pretty salty. So that tells you that the salt is more concentrated as you add more to the solution. So molarity is just a way of quantifying the concentration of a solution. And the way that it's defined is as follows. So molarity is going to be moles of solute, moles of whatever is dissolved. And again, we can define this for the whole compound that's dissolved, or if it's an ionic compound, we can define it for a specific ion as well. So it can be moles of anything that's dissolved in the water or the solution divided by liters of solution. So it's moles over volume, where the volume specifically is in liters. And the key thing too to realize, which isn't always going to be terribly important, but it is precisely defined in this way, is that this is the liters of the solution you have, not the liters of solvent that you use to define it. Now, in most cases, the volume of water that you use to dissolve something, that's going to be the total volume of the solution to a good approximation. But in reality, molarity is defined as the total liters of the solution you have. Because if you dissolve, a bunch of salt in 1 liter of water, the final volume of the solution is not going to be exactly 1 liter. And molarity is defined by how much volume of solution you have, although to a good approximation, the volume of the solution is going to be equal to the volume of the solvent, because in most cases the solvent takes up most of the volume. But it is defined per liter of solution, so it's important to realize that as a sort of matter of being precise. So the abbreviation for molarity is capital M. So when we define the molarity of a solution, it's going to be the number of moles of solute over liters of solution. And this is what we would call an intrinsic property. So it's kind of like density, or it's kind of like mass percent we talked about earlier, where the molarity of a solution is independent of how much of that solution you have, because it's a ratio of moles over volume. So if you have 1 drop of a solution, it's going to have a certain molarity. If you have a whole bucket full of that same solution, the molarity will be the same. It's an intrinsic property. All right, so as an example, just a really simple one to start with, if we have 2 moles of solute and we dissolve that in 1 liter of solution, we would say that this is a 2.0 molar capital M solution. All right, so if a solution is labeled as 2.0 capital M, that means there's 2.0 moles per liter of that solution, of whatever the solute is defined as in that case. Okay, so that's going to be what we use molarity as, and as you can see, because it's a ratio of moles to liters, it is now a new conversion factor we've introduced that involves moles again as another relationship. So when we get to the end of this chapter and start talking about stoichiometry of aqueous reactions, then we'll see that this molarity is going to be used quite a bit for that topic, because it's a relationship involving moles that we can add in to the other relationships that we've already been dealing with. All right, so let's do just one example of this, a fairly simple one. Okay, so we want to know, what is the molarity of a solution prepared by dissolving 15 grams of sulfuric acid, H2SO4, in enough water to form 200 milliliters of solution? Now this picture here is not sulfuric acid. This is what happens if you add sulfuric acid to paper or cotton. It just tears it apart. So it's pretty nasty stuff. So if you're working with sulfuric acid in the lab, don't bathe yourself in it. I would certainly not recommend that. It will destroy clothing, and it will do a number on your skin as well. But anyway, that's not important for this problem. We just want to calculate the molarity of the solution. So when we're calculating molarity, of course, we have to remember the definition of what that is. So molarity, capital M, is moles of solute divided by liters of solution. All right, so we need those 2 numbers to put in here. Now, none of them are given to us directly. We're told how many grams of solute we have. We need to get that into moles. And then we're also told that we have 200 milliliters of solution, which is not in the right unit. So the easier of those 2 is the denominator here, because the liters of solution is 200 milliliters is the volume we're given. We just have to convert that into liters by just dividing by 1,000. All right, so you'll get pretty good at converting milliliters to liters because milliliters is probably a more common unit when we're measuring solutions, but molarity is defined in terms of liters, so we have to convert between those very often. So it's going to be 0.200 liters of solutions. That's going to be our denominator. And then what we have to do is find the moles of solute that are dissolved. And the moles of solute is not given to us directly, but it's going to be, again, a simple relationship that we've already covered, which is converting mass into moles. So the moles of our solute, which is sulfuric acid, H2SO4, we start with the quantity we're given, which is grams, and we just have to convert that into moles using the molar mass. All right, so those relationships involving mass and moles don't completely go away. We just use them again here to get from grams back into moles. And so the molar mass is 98.1. That's given to us directly here. And so that's going to be 0.153. All right, so that's moles of solute. So we're going to put that back up into here, into this relationship for molarity. Moles of solute, which you just calculated, 0.153, divided by liters of solution, which is 0.2, and that means the solution molarity is 0.765, capital M for molar. Okay? So that's how we calculate molarity. And again, we're going to use molarity later on as an important relationship for stoichiometry, so it's not going to go away. But for now, that's all we're going to do with it, just learn how to calculate it for the moment. Okay, so any questions on calculating molarity? Pretty straightforward. You have to make sure that you get the units right, especially for the volume in the denominator, which has to be in liters for this to work. Okay, so with that, what we're going to do is talk about another concept related to molarity, which is dilution. And so what we're doing when we dilute something, I think we have, at least again, a conceptual idea of what it means to dilute something. You're basically taking a solution that has some concentration, some molarity, and you're adding more solvent to it to make it less concentrated. So let's draw a picture of what that means. So you're going to start with the solution here. That's a smaller volume. And what I'm going to show explicitly in this solution are the solute molecules or solute particles that are dissolved with little red dots. So I'm going to keep close track of how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 solute molecules in there, let's just say. All right, and so this is our initial solution that we have. And so then what you do for dilution is you mix this solution with pure water, or pure solvent, whatever the solvent is, but we're going to do aqueous solutions here. So we'll say it's water. So you mix the solution with pure water, or vice versa. You add the pure water to the solution, whatever order you want to do it in. And so what you generate then is a new solution that has a larger volume. All right? But when you've done this, you're not changing the number of solute particles, because all the solute particles that are present in your initial solution are getting mixed in to the new solution just with more water added to make the total volume larger. So you're still going to have the same number of solute molecules. You're not reducing or increasing those. There's still going to be 10 of those. Hope I can still count to 10. So there's still the same number of solute particles, molecules, ions, whatever it is, dissolved in the new solution. So what you have then is your initial solution has a larger molarity because there's the same number of moles in a smaller volume. So it's larger molarity and smaller volume. All right, so it's a larger molarity and a smaller volume for the initial solution, and then the solution that you prepare after dilution by mixing with pure solvent is going to be a smaller molarity and a larger volume. All right, and that's what it means to dilute. You're changing the concentration of the solution, but you're not adding any additional solute, you're not doing any sort of reaction, it's just changing the concentration of a single solution. Okay? So let's just define that again in words now, write it out. So you're adding pure solvent to a solution or vice versa to change the concentration. So that's what we're doing in dilution. So you're either adding pure solvent to a solution or you're adding a solution to pure solvent. Doesn't really matter how you mix them. and all you're doing is making a lower concentration solution. All right, so there's no chemistry happening here. This is just a physical process changing the concentration. And it's important to realize in the way, again, the reason that I drew it out this way, showing explicitly the solute particles that you have, is that the moles of solute stays the same during the dilution process. You're not adding or subtracting solute, you're just changing the volume of the solution to change the molarity. So however many moles of solute you have initially, you're going to have the same number of moles of solute after the dilution. Okay, so that's the concept of dilution. That's what it means. The part that we're going to deal with most often in this course is the mathematical relationships that are involved with dilution. Really one key one that's very simple here. So let's talk about the equation then that's related to dilution. Okay, so as we talked about, the definition of molarity is moles of solute divided by liters of solution, volume of solution more generally. If it's going to be molarity, it has to be in liters. So then what you can do is you can cross multiply this and rearrange. So if we just multiply both sides by volume, we get that molarity times volume, if volume is in liters in particular, is equal to moles of solute. So we just rearrange this relationship to say that the molarity times the volume is equal to moles of solute. We also recognize, as we just said, in a dilution problem, the moles of solute stays the same. So the initial number of moles that you have before dilution is equal to the moles that you have after dilution. So moles initial is equal to moles final. Both of those number of moles is given by the respective molarity and volume. And so then what you can do is set those two equal to each other. M1 V1, where M1 is the initial molarity and the initial volume, is equal to M2 V2, where M2 is the final volume and M2 is the final molarity and V2 is the final volume. So the product of molarity and volume before and after dilution has to be the same because we're not changing the number of moles of solute. So this simple equation here is what we call the dilution equation, and this is what we're going to use. Yes? The volume does change, so V1 and V2 are different. It's the moles that don't change. So the moles of solute stays the same before and after, which is why we can set those two products equal to each other, because moles is equal to molarity times volume. So on each side of the equation, M1, if you define this as the more concentrated solution, M1 is going to be bigger, V1 is going to be smaller. On this side, M2 is going to be smaller, V2 is going to be bigger than the original. Okay? So that's how the equation is set up, and it's pretty simple to use. Now an important thing to realize with the molarity equation, or the dilution equation too, is that volume doesn't technically have to be in liters for this. It can be. You're welcome to put it in liters if you're more comfortable doing that. But because we have volume on both sides, as long as the units are the same on both sides, it doesn't matter if they're liters, milliliters, or anything else. Because when we rearrange this, we would divide by volume, and the two volume units would cancel out as long as they're the same. So you don't have to use liters for this, but you can. And the other thing that's important about the dilution equation is making sure you know when to use it. So you only want to use this when you're doing a problem that involves dilution, which again means you're just taking a single dissolved compound, some solution, and you're adding solvent and changing the volume and changing the molarity. You don't want to use M1 V1 equals M2 V2 when we're doing stoichiometry at the end, where we're reacting two things with each other. It's tempting to use it in that situation, and there are some professors that sort of teach you to do that, but it's risky to do that because it doesn't always work, especially if your reaction has coefficients that are not 1 for every reactant and product. So you need to use this with caution, only use it for dilution, not for anything else. But it's a very powerful relationship for dilution, and mathematically a pretty simple one to use because it's just 4 terms like this. All right, so let's just see then how we would use this equation as an example. So we want to know what volume of 6 molar NaOH is needed to prepare 250 milliliters of 0.5 molar NaOH. Now, which molarity and which volume you define as M1 and V1 and M2 and V2 is up to you. It doesn't really matter. You just have to make sure you're consistent. So we're looking for a volume, so that's our unknown. Let's call the unknown volume V1, although we could also call it V2. and we're looking for what volume of this solution. So this is going to be the molarity that corresponds with that volume. So if I call that V1, this is M1. And we're trying to prepare a solution that has a given volume of 250 milliliters. So that's going to be our V2, and a smaller molarity, 0.5 molar, that's going to be M2. Okay? So in problems that involve dilution, typically you're going to have, there's 4 parameters, M1, V1, M2, V2. One of them is going to be your unknown. You just have to solve for it. So here we're looking for an unknown volume, which we can define as either M1 or V1. So M1, V1 equals M2, V2, and we're solving for our unknown, which we defined as V1. So V1 is just going to be M2, V2 divided by M1. Okay? So the molarities need to be in molar units, capital M, that you can't change. But again, the volume can be whatever you want it to be for this equation. So when we solve for V1, we have M2 is the final molarity that we want, which is 0.5 molar. V2, which is the final volume of the solution, 250 milliliters. Again, whatever your volume unit you want, just make sure you keep track of it so you know what your answer is going to come out in. And then M1 is in the denominator. That's the initial molarity of the more concentrated solution, which is 6 molar. All right, so molarity cancels out, and we're going to get an answer in milliliters, which is 20.8. All right, so that's the volume of the more concentrated solution we'll need, where after we dilute it to 250 milliliters, the final molarity is 0.5 molar. All right, so that's just a pretty typical use, a pretty typical application of that equation in a rather straightforward sense. So it's not going to be much more complicated than that with dilution. Again, the key is to make sure that when you're doing this, you don't use the dilution equation when you're not supposed to, and in some cases we might not directly give you the initial molarity. You might have to calculate it using things we've already talked about earlier today, so it's not always going to be quite this straightforward, but this is pretty typical. So any questions on that? Okay. All right, so for now we're going to leave molarity behind. As I said, we're going to come back to molarity quite a bit at the end of this chapter, which we should get to most of that next time, but we're going to talk about a lot of stoichiometry stuff in this chapter as well. But as I said, I'm going to save that for the end, and so that's going to use molarity a lot. But for now, we're going to just move on to some of the more conceptual topics in this chapter, which are the different types of chemical reactions we can have in aqueous solution. So we're going to talk about 3 categories of chemical reactions in aqueous solutions. And the first of those that we're going to start with now is precipitation reactions. Okay? So let's talk about what a precipitation reaction is. So what happens in a precipitation reaction is we're taking 2 different solutions. So each reactant is dissolved in a solution of usually water again. And each reactant is soluble in that solution. So we combine 2 solutions where the reactants are both dissolved in those solutions. But then during the reaction, whenever a reaction happens, one or sometimes more than one insoluble products forms. And when you form an insoluble product, we call that the precipitate. Okay? So you're either part of the solution or you're part of the precipitate. That's how to remember that. Really? Nobody? Okay, so whatever's dissolved is in the solution. Whatever ends up not being dissolved at the end of the reaction is called the precipitate. That's why I call it a precipitation reaction. It has nothing to do with weather. So that's going to be a precipitation reaction. Now, the type that we're going to mostly talk about in this class are when you mix 2 soluble ionic compounds together, and one of the products, which is ionic compound also, is insoluble in the water and sort of falls out of solution. So that's the most typical one. Now, you can have precipitation in other types of reactions as well. It can be a part of an acid-base reaction that we'll talk about a little bit later today, or it can even be part of a redox reaction, which we'll talk about next time. So precipitation can kind of come up in all of these different concepts, but as a sort of specific reaction class, it would just be, again, 2 ionic compounds mixed together, forming one or sometimes more than one product that's insoluble. So if you remember, I'm not going to show the video again because I don't have it pulled up and I don't want to crash my tablet, but on the I think it was the very first day of class, I showed you a video demonstrating the law of conservation of mass, where they They mixed together two colorless clear solutions, and they weighed the solution before and after the reaction and showed that it stayed the same. And during that reaction, the two colorless solutions mixed together and they formed this sort of cloudy yellow mixture. That's what a precipitation reaction looks like. That's when you have, and actually we're going to talk about that exact same reaction here right now when we go through the example. But basically, again, two soluble things, two clear solutions mixed together, and you form a precipitate, which is a solid that'll just sort of fall out of the solution and either make it look like it's a cloudy mixture, or the solid eventually will sort of sink to the bottom and you'll see it there. So it's a pretty visually obvious type of reaction when it happens. So let's talk about the steps then to determine if a precipitate will form. So what we're going to have you eventually doing in this is we're going to tell you we're going to mix these two ionic compounds together in solution, and you have to predict whether they will form an insoluble product or not. And that's kind of the key idea. So the way we do this is we're going to separate the reactants into their constituent ions. So as we talked about, when you dissolve ionic compounds in water, they separate into ions. So it's important to keep track of what those ions are when you're talking about precipitation. Okay, so the example that we showed in the very first day of class, that video that was a demonstration of conservation of mass, what they were doing in that was mixing together potassium iodide. And so initially the two reactants you mix together are going to be dissolved in an aqueous solution. That's how you always start out with in precipitation. So in that case it was potassium iodide and lead nitrate, lead 2 nitrate, PbNO3 2. And so what we have to keep track of is what ions are formed when these two compounds are dissolved in water and then mixed together. So again, the potassium iodide separates into K plus and I minus. And then lead nitrate, when it dissolves, is lead 2 plus, Pb2 plus. And then we have two NO3 minuses because it's a salt that has two anions in it. Okay, so those are going to be the ions that form when these two substances are dissolved together in water. And again, for predicting whether or not a precipitate will form, the stoichiometry is not critical. Like, if we forgot the two there, we would still come to the same conclusion. But again, for getting the balanced reaction correctly done, then we need to make sure we keep track of how many of each ion there are. And then what we're going to do is we're going to consider the other combinations of cations and anions. So basically we're going to swap the cations and anions with each other and think about the usually two products that can form. So when we mix two compounds like this, you're usually going to have two possible products that can form. And so when we mix these two together, the cation from the first ionic compound, which is K plus, is going to combine with the anion from the second reactant, which is NO3 minus. So one of the products is going to be K plus combining with NO3 minus to form a new ionic compound, which would be just KNO3. And in the other product, we're going to take the cation from the second reactant, which is lead 2 plus, and combine that with the anion from the first, which is I minus. So again, we're just swapping the cations and the anions with each other. So if lead 2 plus combines with I minus, the product that it makes is PbI2. We need to have two iodides to balance the 2 plus charge for lead. So we're not changing the charges of any of the cations or anions. Whatever the cation and anion charges are, when you dissolve them in solution, that's not going to change. So it's lead 2 plus when we dissolve it, so it's going to combine with just the other anion, which is I minus, to make the new product PbI2. So then once we know what the two products are, KNO3 and PbI2, we need to decide whether either or both of these is insoluble. So the way we do that is with everybody's favorite general chemistry topic, solubility rules. All right, and it's not solubility rules like it's not like O'Doyle rules. It's like solubility rules is in a set of rules that we use to predict when something is soluble or insoluble. Okay, so we're going to use a set of rules to help us predict whether an ionic compound is soluble or insoluble. Now, as you'll learn in Chem 2, this is a bit of an oversimplification. Everything has some level of solubility. You can always dissolve some amount of compound in water, but whether it's classified as soluble or insoluble depends on whether it's pretty easy to dissolve or only for a tiny bit. And usually the cutoff, I think, is about 1 milligram per liter. So if there's something that dissolves less than 1 milligram per liter of water, we would typically classify that as insoluble. If it's more than that, then we say it's soluble. There's obviously some things that are kind of in the intermediate range. So you'll learn later on that it's not quite a simple, bifurcation between soluble and insoluble, but in this class, that's how we're going to treat everything. It's either going to be soluble or insoluble, and we're going to use a set of rules to predict that. All right, so the way that I like to divide up these rules is into a few categories. So your book kind of just lists them out, and I have a reproduction of that a little bit later. It just lists out a bunch of rules. If you try to sort of memorize those, it's going to be a little bit challenging, a little bit tedious to do that. So what I like to do is sort of break it up into a few different categories that helps us quickly identify, in most cases, whether a product is going to be soluble or insoluble. So the first one, which I'll call the category A, this is just my sort of categorization. This doesn't really mean anything. It's just the way that I break it up, are cations and anions that are always soluble. So if you find one of these cations or anions in an ionic compound, that compound will be soluble. It doesn't matter what the other cation or anion that it's paired with. So there's a bunch of cations that fall into this category, and most of them are the group 1A alkali metal cations. So lithium plus, sodium plus, K plus, rubidium, cesium, and so on. So all of those group 1A cations, whatever anion they're paired with, whatever the anion is that you're combining them with to make an ionic compound, those compounds will be soluble. So that will not form a precipitate. Whatever is soluble is not the precipitate, okay? So anything that has these cations in them will be soluble. And there's also one other cation that behaves the same way. It's a polyatomic. So one of the few polyatomic cations we had, NH4+, which is called ammonium. So ammonium, in the same way as the rest of these, if that's part of an ionic compound, you can just assume that that compound will be soluble, okay? So those are ones that are always soluble. And then there's some anions that would fall into this category as well. So nitrate, NO3-, perchlorate, ClO4-, and then acetate, which can be written either as CH3COO- or sometimes more simply as C2H3O2-. That's called acetate. Those anions are always in soluble ionic compounds. So if you have this anion, no matter what the cation is, you will assume that the compound is soluble. So those are the first ones you want to look for, because if you see any of these cations or anions in your product, you can know then that that product is going to be soluble. It's not going to be the precipitate that forms. And then there's another category, which would be cations and anions where their salts are always insoluble unless they're paired with one of those in category A. So the two classic cations that fall into this category are silver plus and lead 2+. Okay, so every silver plus salt and every lead 2+ salt is insoluble unless the anion is NO3-, ClO4-, or acetate. So again, if it's paired with one of these anions, it will be soluble, but if it's paired with any other anion, these will be insoluble in whatever compound they form. And then for the anions that fall into this category, you would have carbonate, and some of these are more common than others. So like you'll see you'll see lead and silver all the time. You'll see nitrate all the time. Carbonate you'll see sometimes, phosphate sometimes. Sulfide is a pretty common one that's usually insoluble, and then chromate, that one we'll see all the time. But these are the four that I would put in this category, where if you have this anion as part of your ionic compound, it's going to be insoluble unless the cation is one of these up here, the group 1A or ammonium. Okay, so sodium carbonate would be soluble, but carbonate with other cations like calcium or any of the transition metals would be insoluble. So unless the cation is one of these, any salt with carbonate will be insoluble. So those are the categories where you want to look for first, because again, these will always be soluble. These ones, you're usually going to have an insoluble product form, except for the rare exceptions from above. And then the rest of these rules are kind of, a little bit more annoying, because they're kind of the in-between cases where sometimes they're soluble, sometimes they're not. But there are some anions and cations that are, and specifically anions, that are usually soluble unless they're paired with one of those cations that's always insoluble. So if we have the halide salts, in particular the three heavier ones, Br-, Cl-, and I-, halides. Yeah, so those are the group 7 anions, that sort of second to last column of the periodic table. So chloride, bromide, iodide. those salts, if they're in an ionic compound, they're usually going to be soluble unless, again, the cation is silver or lead. So these are sort of a hierarchical precedence. So category B, you want to think about that first. But if it's any other halide salt where the cation is not from one of those. Now there's two other exceptions you should be aware of for halides, which won't come up as much as lead and silver, but just to be aware of. So copper plus, if it's paired with any of these, so if it's copper chloride, copper bromide, copper iodide, and if you have this diatomic mercury cation, again, one that we've introduced but is not like terribly common in this course, but you might see it. Don't want to promise that you won't. These are also insoluble halides. Okay, so copper 1 with chloride, bromide, iodide, or mercury, the diatomic mercury 1 cation, which has chloride, bromide, iodide, those would be insoluble as well. So those are a couple other exceptions, but again, halides are pretty much always going to be soluble unless it's silver halide or lead halide, those two cations that are always insoluble. And then the ones that are really sort of annoying, I suppose, are these ones here, and there's not really a great way of categorizing them, but just to remember them. So the two that I'm going to put in this category are sulfate and hydroxide. So sulfate, SO2 minus, SO4 2 minus. These are usually soluble more often than not, except when they're with those category B cations, lead and silver. And there's other exceptions as well that we need to be aware of. So the heavier alkaline earth cations, calcium, strontium, and barium. So these are the heavier group 2 cations. Those with sulfate are insoluble. And also sulfate with lead and silver are insoluble. So there's, again, usually a soluble compound with sulfate, but more exceptions than the other ones that we have to be aware of. And then the other one that's in the same category, it actually has the same exceptions, but it's sort of in the opposite direction. So sulfate is usually soluble. Hydroxide OH minus is usually insoluble. Except when it's with the following. So again, those category A cations, lithium, sodium, potassium, rubidium, cesium, and ammonium. So those ones are always soluble, and that's true if it's with hydroxide. But then they also have the exceptions, the same exceptions as above, but again, the opposite direction. So calcium, strontium, and barium are also exceptions for hydroxide, but in this case, those are soluble, whereas in sulfate, those are insoluble. So those are the harder ones to remember. So I'm not going to lie that those are annoying and not try to sugarcoat that in any way. But again, for most problems you're doing, you can get most of the way there by just focusing on those first two categories. The cations and anions that are always soluble, or the cations and anions that are always insoluble unless they're with one of those always soluble partners, okay? So you have to learn these a little bit, you have to practice them, there's no real shortcut around it. But as I said, breaking it up into categories like this is helpful. So if you don't do it this way, this is sort of how your book does it. They just list out 6 rules that seem kind of randomly organized, and so I'd like to break it down a little bit simpler the way that I did it, but however you choose to learn it, you'll get the same place either way. All right, so I guess I'll pause for any questions on solubility rules, although again, it's mostly one of those things you just have to kind of internalize. There's not a lot of logic to it, unfortunately, at this stage. Yeah? Yeah, silver and lead are the cations from category B. So that means if you have an ionic compound with silver and lead, it's going to be insoluble unless the anion is one of these 3. Okay, so any other anion. Because we don't add them together, it's just either, I should say or, maybe is a better way of saying that. Silver or lead. So, your ionic compound is always going to have, these are going to be compounds that have one cation and one anion, where the anion could be polyatomic in a lot of cases. And so again, these rules are for individual ions, and whatever they're paired with, you have to consider as well. So as I said, for silver and lead, if they're paired with nitrate perchlorate acetate, they will be soluble because that rule takes precedent, but silver or lead with any other anion will be insoluble. So that's kind of how you want to think about that. So the compound will have one of those two cations and not both. It's always going to be just a single cation present in the compound. All right, anything else? Okay, so let's just talk about then how we use them to make predictions about precipitation reactions. So we can now write out the precipitation reaction in a few different ways that we're going to talk about. So there's the molecular equation, the total ionic equation, and the net ionic equation. I think the first and the third are the more common one. Total ionic is kind of unwieldy in most cases, but it can be useful to consider, at least in some cases. But we're going to learn how to write these ionic equations in a few different ways. So the molecular or formula equation is the full set of reactants and products. And this is probably the most common way of writing it out. Where it's going to look like a typical chemical equation. There's really nothing different about that. So in a molecular equation, you just write out all the reactants and products, and you write them as sort of intact ionic compounds. You don't separate the ions in a molecular equation or formula equation. All right, so talking about the example we've been working through, if we take aqueous potassium iodide and react it with lead nitrate, what we saw earlier is that the two products that form are going to be the ones where we swap the cations and the anions. So potassium is going to pair with nitrate to make KNO3, and then lead is going to pair with iodide to make PbI2. And then to figure out on the product side whether these are going to be aqueous dissolved compounds or precipitates, meaning that they fall out of solution, we have to think about the solubility rules. So in the solubility rules, we saw that all potassium salts and all nitrate salts are soluble. So this one will definitely remain soluble and be written as AQ, meaning that that compound is still dissolved. But then for lead iodide, we saw that in almost every case, lead compounds are insoluble unless the anion is nitrate perchlorate acetate. So lead iodide would be insoluble. So we want to write that as S for solid, meaning that it comes out of solution as a solid. It's no longer dissolved as an aqueous ionic compound. So that's the reactants and products, but we need to balance it. So we have two iodides on the right side, so we need to have a coefficient of 2 here to balance iodide. And then we have also 2 potassiums and 2 nitrates, so we need a coefficient of 2 there to balance the potassium and the nitrate. For these problems, I think it's usually helpful to just balance the individual ions, not the individual atoms in this case, just because the polyatomic ions are going to stay together. They're not going to break up in any way. So we have 2 nitrates here, 2 nitrates there, 1 lead, 2 iodides from PbI2, 2 potassiums, 2 potassiums. So the coefficients for these types of equations are usually pretty small and pretty simple. 1, 2, maybe 3 at the most. You're not going to see huge coefficients, but you do need to make sure they're included to balance it. So that's going to be the sort of the molecular equation, probably the most common way that it'll be written. But there are 2 other ways we can also write ionic equations. So one of them is called the total ionic equation, where we're going to separate all of the soluble ionic compounds into their individual ions. So those are going to be the ones that are marked as AQ, because remember that AQ means dissolved in water. When an ionic compound is dissolved in water, it splits up into its 2 individual ions. So for this equation up here, to write the total ionic, potassium iodide is aqueous, it's dissolved, so we're going to separate that into 2 ions, 2K plus and 2 I minuses. There's 2 full Ki, so each one's going to form 2 cations and anions total. So 2K plus 2 I minus. Lead nitrate is a soluble compound, so it's going to be written as lead 2 plus and 2 NO3 minuses. So we separate both reactants into their ions because they're both soluble ionic compounds. And then on the product side, we have one of our products, KNO3, is soluble, so it's written as AQ. So that's going to also be separated into ions, 2K plus and 2 NO3 minus. But then the second product, which is PbI2, is again a precipitate. It's written as solid here, so that one we don't break up because it's not dissolved anymore. So for total ionic equations, we separate the ionic compounds into their ions if they're soluble and dissolved in water. So we don't do that for PbI2 because that's no longer dissolved in water at the end of the reaction. Okay, so that's the total ionic equation. That one's not particularly useful, but it will be shown sometimes. But what it is helpful for is if you write the total ionic equation, it makes it much easier to generate what's called the net ionic equation. So the net ionic equation, what you do is you remove what are called spectator ions. And those are going to be ions which appear on both sides of the arrow as dissolved ions. All right, so if we go back up to our total ionic equation, we see that we have 2K plus on the reactant side, and we have 2K plus on the product side. So in net, nothing is happening to K plus. It's just staying dissolved in the solution the whole time. So this is one of our spectator ions. I'll mark the spectator ions with an X here. And then the other spectator ion we see is NO3 minus. There's two NO3 minuses here on the reactant side on the left side of the arrow, and on the product side there's also two NO3 minuses. So that ion is dissolved aqueous ion on both sides with the same coefficients. That would be another spectator ion. So what we do for the net ionic equation is we leave out the spectator ions and we only write out the ions that combine to form our precipitate. So what's left over then is conventionally you write cations first, so it's going to be lead 2 plus 2 I minuses combining PbI2. So in this reaction here that we're considering, K plus and NO3 minus are the spectator ions. All right, and that means they just stay dissolved in the solution the whole time, and they don't participate in the net reaction, because the net reaction is forming lead iodide as a precipitate, which involves the combination of lead 2 plus and 2 I minuses. So this would be the net ionic equation, just showing the ions that combine to form whatever the precipitate is on the right side of the equation. All right, so any questions on how to write those different equations? As I said, the most common one we'll ask you to do is probably the first one, the total equation, or the bottom one, which is our net ionic. Those are the ones that are usually the most useful and the most commonly encountered on homework assignments, but the total ionic equation is helpful for getting to the net ionic correctly, okay? So let's just do some examples of this. So we're going to have here, we want to write all three equations, the molecular, total ionic, and net ionic equations for the reaction that occurs between sodium sulfate and silver 1 nitrate. All right, so for these, we do need to make sure we have the formulas of the compounds correct, because if we're going to write the correct chemical equation, the formulas of the reactions and products obviously have to be the same. So we learned back in chapter 3 how to name and determine the formulas for ionic compounds, so we have to make sure we remember that. So for sodium sulfate, if we go to the periodic table, we find that we should know by now that sodium is one of our group 1 cations, so it's going to form a +1 cation, and then sulfate is SO4 2 minus. So the formula for sodium sulfate, we have Na plus SO4 2 minus, so the formula for that is going to be Na2SO4. And then for silver 1 nitrate, we already saw that reactant, I think, or something earlier. Silver 1 nitrate is silver plus with NO3 minus is nitrate, so the formula for that is just AgNO3. Okay, so we do need to make sure that we can correctly get the formulas of ionic compounds if we're going to do this. And from there, we can start writing the different equations. So the molecular equation is going to write out all the reactants and products as intact ionic compounds. So on the reactant side, we have sodium sulfate, Na2SO4. The reactants are always going to be aqueous solutions for these types of reactions. And then silver nitrate, AgNO3. And then remember, when we predict the products for these reactions, we just swap the cations and the anions with each other. So the cation from the first reactant is Na plus. The anion from the second reactant is NO3 minus. So Na plus combines with NO3 minus to make NaNO3. We don't change the charges of any of them. And then the second product, we're going to take silver plus and combine it with SO4 2 minus. So the correct formula for that would be Ag2 SO4. All right, so then we have those reactants and products, and then we have to predict whether they're going to be soluble or insoluble to write the correct designations for those. So NaNO3, sodium always soluble, nitrate always soluble, so that compound is definitely always going to be soluble and written as AQ. If anything that has sodium or nitrate in it would be soluble. And then for silver sulfate, we said silver is one of those cations that is almost always insoluble unless the anion is nitrate or perchlorate or acetate, nitrate being the most common. So this would be one of those that's going to be insoluble. So again, usually if you see silver or lead, you want to sort of focus your attention on that as being part of the precipitate. So that's our molecular equation. We do need some coefficients to balance. So on the left side, we have 2 sodiums. So we need a coefficient of 2 there. And now we have 2 nitrates. So we need a coefficient of 2 there. And that will also then balance silver, 2 there, 2 there. So again, pretty small coefficients generally are needed, but it's often going to be something that's not just 1. So we have to make sure we're balanced. So that's the total or molecular equation for this. We write out everything intact. We indicate which ones are soluble and insoluble. For the total ionic equation, which is not as useful, but we're asked to do it here, we again separate all of the soluble ionic compounds into their individual ions. So on the reactant side, we're going to separate both reactants. So sodium sulfate is going to separate into 2 Na plus and SO4 2 minus. We're going to separate the second reactant into its ions. We have 2 silver nitrates, so those are going to dissolve to make 2 silver plus and 2 NO3 minuses. The coefficient applies, of course, to both ions in the compound. And then on the product side, our first product, sodium nitrate, is still a soluble ionic compound, so it's going to be 2 Na plus and 2 NO3 minus. But then our second product, silver sulfate, is insoluble, so it's going to still be written as Ag2SO4 solid. We don't separate that because it's no longer dissolved in the solution. So that's our total ionic equation, where we just separate out the soluble ionic compounds into their constituent ions, and then finally the net ionic just requires us to remove the spectator ions. So if we look at this equation, the total ionic, we have 2 Na plus on both sides, and we also have 2 NO3 minuses on both sides. So when we write the net ionic equation, those ions get left out, and we just keep the ions that combine to form our precipitate. So the net ionic equation is going to be 2 Ag plus, and again, conventionally we write the cations first, then the anions, but it wouldn't be wrong to do it the other way, plus SO4 2 minus, and then the product that's left when we remove the spectator ions is Ag2SO4 solid. Okay, so our net ionic equation for precipitation reactions is just whatever ions combine to form the insoluble product. All right, so I think that takes us to the end of precipitation reactions. So any questions on that before I move on? So again, the key thing you have to do is learn those solubility rules, because a lot of the problems, either the whole problem or at least part of the problem, involves you predicting which product would form and which one would be insoluble and be your precipitate. So that's make sure something you can do well. You're not going to see that until next week's homework assignment, which I guess is probably after the break, I think. I don't think we give you one that's due during the break. So anyway, you have a while to learn this stuff, but it's coming up soon after the break. All right. So if there's no other questions on that, we'll move on to the second reaction type, which is acid-base reactions. Now, on some level, acid-base reactions look kind of similar to precipitation reactions. You no longer really have ionic compounds involved, or usually only one of the reactants is ionic, but you're still sort of, in some sense, swapping cations and anions with each other in a similar way, but the net outcome is a little bit different. And furthermore, for acid-base reactions, you can also have precipitation as part of the reaction, but it doesn't have to be involved. So again, depends on what the products are that form. You might get an insoluble product that forms a precipitate, but in most cases you won't. All right, so let's first do some definitions to make sure we understand acids and bases. Now, we talked in chapter 3 also about acids in particular, how to identify what they are, how to name them, what their formulas are. So we kind of know what they look like, and now we're going to talk more about their chemistry. So an acid is a compound that releases H plus when it dissolves in water. So even though hydrogen is a nonmetal, you can form what looks or essentially behaves like an H plus cation when certain substances are dissolved in water. So when you dissolve an acid in water, you release H plus. And you're going to go into a lot more details on acids and bases in Chem 1312, the second semester of this course, if you take it. So it's, a lot more is coming. For now, we're going to just, again, scratch the surface for what we're doing here. But we have to recognize that an acid is a compound that releases H+ when it's dissolved in water. And as we already discussed in chapter 3, the formula of an acid is going to look like this. It's going to be some number of hydrogens at the front of the formula paired with an anion X. And again, N is the charge of the anion, which then dictates how many hydrogen ions it needs to be paired with to write the correct formula. All right, so classic acids are things like HCl, HBr, or H2SO4. Hydrogen pair with many of the common anions that we know about from ionic compounds. Now, the other half of this acid-base reaction will be the base itself. So a base is a compound that releases OH- when you dissolve it in water. Now, there are a lot of potential substances that can classify as bases, but the ones that we will pretty much exclusively see in this course are just going to be ionic hydroxide compounds. So some metal cation paired with hydroxide anions. So sodium hydroxide, lithium hydroxide, calcium hydroxide, whatever hydroxide salt you can imagine, those would be what we're going to classify as bases. Where N is going to be, again, the charge of the cation that dictates how many hydroxide ions are in the formula. All right, most of the common bases, as we said, are going to be those group 1 hydroxides.
Is that charge?
Charge, yes. Yeah. So it's going to be the charge of the Mn+, whatever the cation is. So it's usually going to be 1-to-1. It's usually going to be like lithium hydroxide, LiOH, sodium hydroxide, NaOH, something like that. But it can be a more complicated formula if the charge of the metal is not +1. So those are what acids and bases look like. And again, that's kind of how we define them. So then when we also talk about acids and bases, it's helpful to think about as well the difference between a strong acid and a weak acid and a strong base and a weak base, which we've already, again, talked about a little bit earlier, but we're going to see it in more detail now. So a strong acid is an acid or a base that dissociates completely into ions. So when we dissolve a strong acid or a strong base in water, it completely separates into the ions that make it up. And so as a result, we would classify these as strong electrolyte solutions using the terminology we learned at the beginning of this chapter last week. All right, so strong acids and strong bases form strong electrolyte solutions. They completely break up into their ions. So we just have to recognize which acids are strong. There's not really a great way for us to rationalize this at this point. But again, most of those group 7 halide acids are strong. So HCl, HBr, and HI, all but HF, are going to be strong acids in that category. And then some of the polyatomic ones, so nitric acid, HNO3, sulfuric, and perchloric acid. So HCl4 is perchloric, H2SO4, at least for the first proton, can dissociate completely in water, so that would be a strong acid as well. All right, so those are your strong acids. The strong bases are going to basically be, for our purposes, pretty much every base that dissolves in water. So all of these group 1 hydroxides, lithium, sodium, potassium, rubidium, cesium. Remember from our solubility rules that all ionic compounds that have these cations in them are soluble. So these would be soluble hydroxide compounds. So when you dissolve them in water, they completely separate out into the cations and the hydroxides. So that would classify them as a strong base because they completely separate into those. And then there's some of the group 2 ones that are soluble as well, as we talked about in some of the exceptions to our solubility rules. So calcium hydroxide, strontium hydroxide, and barium hydroxide, these are all from group 2. And these are also soluble and would then be classified as strong bases because they dissolve completely in water. So those are basically the full list of bases you're likely going to see for most of the things we do in this course. They're just hydroxide salts, and they have to be ones that are soluble to be able to dissolve and dissociate in water as a strong base needs to do. Now, if we have a weak acid or a weak base, those are going to be acids and bases that do not completely dissociate. And again, this is a topic that you will come back to in a lot more detail in the next semester of this course if you take it. So we're not going to do a lot with weak acids and weak bases in here. But what this means is that when you dissolve one of these compounds in water, most of the molecules are going to still stay together. You're going to get a little bit of dissociation, a little bit of H plus is going to sort of separate from the anion and get some ions in solution, but most of the molecules stay intact. They don't break apart like you do for a strong acid. And that would mean it's a weak electrolyte solution, as we talked about. So these would be classified as weak electrolytes. Because they don't completely separate into ions. And there's just a few common weak acids. I mean, pretty much every other acid besides the ones I listed above are weak acids, and the ones that you'll see a lot of are HF, so that's the only of those group 7 acids that's not a strong acid, and then some of the polyatomic ones, phosphoric acid, and the very classic one is acetic acid, which can be written as CH3COOH, or it can be written as, how would you write this? C2H3O2. HC2H3O2. So it's kind of a weird way of writing it, but both of those are the formula for acetic acid. This one shows more closely how the structure looks. This one just shows the chemical formula. So anyway, acetic acid, acetate paired with H+. And then there's really only one weak base we need to worry about, and I think I mentioned it before, but I'll mention it here again. It's just ammonia NH3. Now you might be wondering, well, how is that a base at all? It doesn't have hydroxide in the formula. And so when ammonia NH3 dissolves in water, what happens is some portion of it, not all of it again, because it's not a strong base, but some portion of it reacts with the water, and you basically get one proton transferring from the water to the NH3 to make NH4 plus and OH minus. So that's what happens when you dissolve NH3 in water. So it does form a little bit of OH minus. Most of it stays as NH3. Most of it doesn't react with the water. But a little bit of it reacts, so you get some ions in solution, including some hydroxide, which is what we classify as a base. All right, but that's the only weak base you need to worry about. And we're not going to do a ton of chemistry with weak acids or weak bases. We're going to mostly focus on reactions that involve strong acids and strong bases. All right, so that's some definitions to start us with. Now let's talk about how they react with each other. So the net ionic equation for every acid-base reaction, particularly when it's a strong acid and a strong base, is going to be the same. Now the only time the net ionic equation is going to look a little bit different is if one of the acids or bases you're reacting is weak. But if it's a strong acid and a strong base, which is the most common we'll see in this course, the net ionic equation is just the H plus from the acid combining with the OH minus from the base. And you have H plus OH minus. Anybody want to guess what the product is? Let's see. What's something that has 2 hydrogen and oxygen in it? Water, right? So H2O, either liquid or aqueous, however you want to write that. But you form water by combining the H plus from the acid and the OH minus from the base. So that's the net ionic equation for most acid-base reactions. What's going on? All right, so the spectator ions that are present and the coefficients in the equation are going to depend on the identity of the acids and bases that you're using. All right, so there's going to, if you're writing the full equation for an acid-base reaction, we don't usually just write the net ionic because it doesn't tell us a whole lot. But if you write the full equation, you're going to have coefficients potentially, and you're going to have different spectator ions. All that depends on what you're actually reacting. So the overall outcome of an acid-base reaction, though, if we write out the full equation, is going to be an acid plus a base as our reactants. And the products are always going to be water. That's, again, the combination of H plus and OH minus makes water. And the other compound the other product is an ionic compound. where the ionic compound that forms is made up of the cation from the base, because remember that 99% of bases are just metal hydroxide salts. Whatever cation the base has combines with whatever anion the acid has to make an ionic compound. All right, so whatever's left over, whatever ions are left over after H plus and OH minus combine, those are going to combine to form an ionic compound. That's going to be your other product. And in most cases, this is going to be a soluble ionic compound, so it will just sort of stay in solution. But again, it is possible for the ionic compound that forms to be insoluble and form a precipitate, so you have to be aware of that possibility as well. So that's how they work. So let's just write out some example acid-base reactions. How many more of these do I have? Am I going to run out of time here? Nope, we got enough time, so let's finish these up. So again, these are usually pretty simple and don't involve very large coefficients. We have to make sure we're writing out things correctly. So if we have nitric acid and potassium hydroxide, this would be about as straightforward as they come. So we have to make sure we get the formulas correct for the reactants. So nitric acid is HNO3. Nitrate is, again, NO3 minus, so it's going to have one H plus with it to make an acid, so HNO3. And then potassium hydroxide, you should remember this by now, but if not, from the periodic table, potassium is group 1A, so it's going to form a +1 cation. Hydroxide is -1, so the formula for that would just be KOH. So those are going to be the reactants, acid plus base. And as we said, the products for an acid-base reaction is always going to be water and an ionic compound. So we're forming water as one product. That's the combination of H plus and OH minus. And then the ionic compound is going to be the cations and anions that are left over. So the cation from the base is K plus. The anion is NO3 minus from our acid. So the ionic compound that forms is KNO3. And that's a soluble ionic compound. K plus salts are always soluble, as are NO3 minus salts. So by solubility rules, that will be a soluble ionic compound. If we look at coefficients here, we'll find that none are actually needed. Now, water can be usually written as liquid, but it doesn't matter too much. But the coefficients here, there aren't going to be any. Everything's 1 to 1 to 1 to 1, because if we're combining one H plus and one OH minus, we form one H2O, and moreover, the ionic compound that forms is just a 1 to 1 ionic compound, 1 K plus, 1 NO3 minus. So we don't need any coefficients to balance this equation. It's just one for every reactant and every product. And again, just like precipitation reactions, the coefficients for acid-base reactions tend to be pretty small. Not always ones, but ones, twos, maybe threes at the most in the worst cases. All right, let's do one for another strong acid, strong base combination, but this time we will have coefficients involved. So if we have sulfuric acid, sulfate is SO4 2-, so the formula for that acid is H2SO4. We need two H pluses to balance the charge on the anion. Then we still have potassium hydroxide, which is still KOH, same as above. And so now let's think about how to balance this. Now there's a few ways we can balance it. Again, the products we can write out first if we want to. So we're going to have H plus and OH minus are always going to combine to form water as part of an acid-base reaction. And then we're going to form an ionic compound from the remaining cations and anions. So we still have K plus from the base, that's our cation in the product. And then SO4 2- would be the anion on the product side. And so that's going to be combined as K2SO4 to get the correct charge. And that will be soluble because all potassium salts are soluble. But this reaction does need coefficients, and there are a few ways you can go about getting those coefficients. The way that I like to do it for acid-base reactions is think about how many H pluses and OH minuses I have. So in my acid, I have two H pluses because it's H2SO4. So if I have two H pluses, I also need two OH minuses because in an acid-base reaction, H plus and OH minus always combine 1 to 1 with each other. So if your acid has two H pluses, you also need to have two OH minuses from your base, OH minuses. And this one only has one, so that means we need to put a coefficient of 2 in front of it to make sure that we have the same number of OH minuses and H pluses reacting with each other. And if two each react with each other, 2 H plus, 2 OH minuses, we form 2 H2O as a product. And we don't need a coefficient here because the K plus is already balanced, SO4 is already balanced. So there are going to be some coefficients, but again, usually pretty small. A few different ways you can go about getting those written out, but that's how it would be for this one. All right, and then the last ones we'll do is involving a weak acid, so we're going to see how it's a little bit different with a weak acid. So here we want to do the net ionic equation for the reaction between acetic acid and barium hydroxide. If it was a strong acid and a strong base, the net ionic equation would always be just H plus OH minus forms H2O. But if it's not a strong acid or a strong base involved, then you need to write it out a little bit more carefully. So acetic acid is a weak acid, so we need to make sure we approach this one a little bit more carefully. So acetic acid is CH3COOH. That's the most instructive way to write the formula. And so acetic acid, AQ, the base is barium hydroxide. I should have mentioned in this problem, barium is Ba, which is in the periodic table here. It's too far down for you to know that, but anyway, it's beyond 36, but it's here, it's group 2, so it's going to be barium 2 plus. So the correct formula for barium hydroxide is BaOH2 to balance the charges. So those are the reactants, and then on the product side, the total ionic equation is going to look very similar for a weak acid and a strong base. Because again, we're just going to take the H plus from the acid, combine it with the OH minus from the base to make water. And then we're going to be left with an ionic compound, which in this case is going to be barium 2 plus combined with CH3COO minus, acetate, however you want to write that. So you need 2 of those. So CH3COO is the formula with a -1 charge, so you'll need 2 of those on the product side. And that will be soluble because all acetate salts are soluble. So then we need some coefficients as well. So if we have 1 H plus from our acid, and acetic acid, only one of the hydrogens is actually as an H plus. So it's important to remember that. Acetic acid is just a 1 proton acid. So 1 H plus and 2 OH minuses. We need a coefficient of 2 there and a coefficient of 2 there to balance the equation. So that's the total, the full molecular equation for this, which doesn't look that much different. It's just acid plus base makes water plus ionic compound. So whether it's a weak acid or strong base, that doesn't matter. But the net ionic equation is going to be a bit different. So if we write out the total ionic first, we have to recognize that acetic acid is a weak acid. And when you write out an ionic equation for a weak acid, we have to remember that for a weak acid, most of the molecules do not dissociate into ions. In a weak acid, they mostly stay together. So when we write that as an ionic equation, we don't separate CH3COOH because it's a weak acid. So that's going to stay as CH3COOH AQ. Again, only a small number of these will actually separate into ions. Most of them stay together, so that's how we write it. But then the barium hydroxide we're going to separate out into ions. So it's going to be barium 2 plus and 2 OH minuses. And then on the product side we have water. That's clearly a covalent compound. We don't separate that into ions. And then we have our product, which is going to be an ionic compound. So it'll be separated as barium 2 plus and 2 acetates. All right, so that's how we write out the total ionic equation. We don't separate the weak acid because a weak acid mostly stays together when it's dissolved in water. But we do separate the ionic compounds, which will be barium hydroxide on the reactant side and barium acetate on the product side. So then when we want to formulate the ionic equation, which is what this asks us to do, what we have in this case is the only spectator ion we have is barium 2 plus. Okay, because barium is written as 2 plus cation aqueous over here. It's written the same on the product side. So the barium sort of cancels out, but everything else needs to be written in the net ionic equation. So for our net ionic, what we get is 2CH3COOH plus 2 OH minuses are left. And then the product side, we have 2 waters and 2 acetates. So this is our net ionic equation. We have coefficients of 2 in front of every reactant and product, so we can actually simplify this. Because it's 2, 2, 2, 2, so we can just write it as a 1-to-1 reaction as well. And that would be the way to balance it with smallest whole number coefficients. So acetic acid aqueous plus OH minus aqueous forms acetate and water. I guess I switched the order of the products, but it doesn't matter. So that's the net ionic equation. It's more complicated when weak acids are involved because the acid does not dissociate completely, and so you write that as an intact molecule, and only the species that dissociate, the ionic compounds, will be written as those, and so on. So it's more complicated, but that's how we would do it for a weak acid reaction. So next time what we're going to cover are redox equations, redox reactions, which is the third major category of aqueous reactions, and those are a bit more tricky to balance, so we're going to spend a lot more time on talking about how to balance those equations next time. All right, so I'll be in my office right after this if you need to come see me, and if not, I will see you guys in class on Thursday.